Okay, so right now what we will do in this class, we will try to verify laws of reflection and laws of refraction using Huygens Principle. Now why it is important? Because reflection and refraction are the phenomena which we already know and that are explained using ray optics, right? Now earlier this man Huygens had a very difficult time in explaining his theory because before him Newton, there was a huge following of Newton's ideas and where people believed that whatever Newton said was the ultimate truth. Okay, but what happened is when he came, he had a difficult time explaining the people that light not just traveled as a ray, but it also travels in the form of waves, right? So he came up with the idea explaining the phenomena of reflection and refraction using the Huygens theory, so that people could believe that there's a theory which could explain these two phenomena also on the basis of wave nature of light, right? But obviously that it's a complex way of explaining these two phenomena, and most of the time we study these two phenomena using the ray optics only, right? So Huygens Principle and laws of refraction. So in this class we will derive the laws of refraction using Huygens Principle, and let us see. So we have taken a mirror. So this is a plane mirror. Let me name this plane mirror as NM. So NM is the plane mirror. This is a wavefront, AB is a wavefront. So this is a wavefront. Why we are using wavefront? Because Huygens Principle is all about the wavefront, light travelling as a wavefront. Now what are these two light? These are the rays. So therefore they are perpendicular to the wavefront, which we have already studied in the previous class, that the light rays are always perpendicular to the wavefront. So this wavefront AB is striking the mirror. Now how it is going to reflect? So basically in the previous class we studied that if this is the wavefront, suppose it is striking at this point, each and every point on this wavefront is acting like a source of a new wave. So it is acting like a source of new wave, which is moving in all possible directions with the speed of light. Again, if we draw a tangent, again these light rays can be drawn on this, again a tangent can be drawn. So this will keep on reflecting and moving in this direction. And how do we know that? Because we already studied that the light rays shows the direction to the wavefront. Okay, basically they represent the direction. So we know that this light ray will come, it will reflect with the same angle. Okay, if this is angle I, this will be angle R, and angle I is equals to angle R, but that is the case for ray. We have to prove the same thing for wavefront, that is AB. Again this light ray is coming, striking this surface, it is going like this. So obviously if these two light rays are going like this, there has to be a wavefront which is perpendicular to these two light rays. So which wavefront is this? This is the wavefront. So actually which wavefront is this? The wavefront AB, which is getting reflected in this direction along with the rays, and that wavefront is now CD. So what is CD? It is the reflection of a wavefront AB. Now we have to prove that this angle I, which this wavefront is making with the mirror, and this angle R, which is the angle of reflection for this wavefront CD, these two angles are equal. We have to prove this, right? So how do we prove it? So we take the help of geometry. So in triangle ABC and triangle DBC. So if you take these two triangles, you say that BC is equals to BC, which is common. Now as you know that the light is travelling in the same medium, it is not changing the medium, because it's a case of reflection. So obviously when it is travelling in the same medium, what will happen? The speed of light will remain same, right? So the distance travelled from B to B and the distance travelled from A to C has to be equal. Why equal? Because the light is travelling with the same speed, right? And by the time this light ray is getting reflected here, in the same time this has to reach here. So therefore, this B distance will be equal to AC distance, and that will be C into T. What is C? C is the speed of light in air or vacuum, which is 3 into 10 to the power 8 meter per second. And what is T? T is the time period, right? Now guys, this angle would be 90. Why this angle would be 90? Because this is 90 here. So if this is 90, this is a straight line, again it will be 90. Why this is a 90 degree? Because light rays are always perpendicular to the wavefront. So if this angle is 90, so which angle would be 90 here? This angle would be 90. Why this angle would be 90? Again the same reason, that the light ray is perpendicular to the wavefront. So angle BAC will be equal to angle BDC will be equal to 90. Right? Now if you look at these two triangles, you could find that this triangle, these two triangles are congruent. So triangle ABC is congruent to triangle DBC. And if they are congruent, then obviously all the angles of these two triangles at all the sides of these two triangles would be equal. Therefore, angle I will be equal to angle R. So this is the law of reflection, that angle of incidence is equals to angle of reflection. So this is the law, first law. And then obviously we can write that the incident wavefront, which is this wavefront, incident wavefront, the reflected wavefront and the normal at the point of incidence all lie in the same plane. All lie in the same plane. All lie in the same plane. So this is the two laws of refraction. This is the two laws of refraction, that angle I is equals to angle R, right? So this is how you can prove the laws of reflection. And now we will move on to the next topic, that is the laws of refraction. Okay, so now here is the diagram to prove the laws of refraction. So you know that this is an interface. Interface is a imaginary surface which separates two different mediums, right? So we are talking about the refraction now. So again the same thing, AB is a wavefront, these are the two light rays refracting, we know they will bend like this will also bend. And now this wavefront, because at a point it started striking the interface only, so it reached here, and this point has reached here along with the light rays, and this CD is the refracted wavefront and incident wavefront is AB. And this is angle I and this is angle R, right? So you know that in refraction we have something known as Snell's law. So mu is equals to sin I upon sin R, we have to prove. Mu is equals to sin I upon sin R, we have to prove. And we know that this mu is what? It is the ratio. Mu is equals to C upon V. What is C? Speed of light in air or vacuum. What is V? Speed of light in some other medium. So we have taken as V1 to be the speed in this medium and V2 to be the speed in some other medium, right? So mu is equals to V1 upon V2. This we know. This is what we know. This is what we have to prove. And this is what we know. What I am going to do, I am going to take this triangle ABC. So triangle ABC. Now if I take triangle ABC, this will be sin I. Why I am calculating sin I? Because I need sin I. Sin I. This is angle. So angle, this will be perpendicular. This is base and this is hypotenuse. So angle, perpendicular, base, hypotenuse. And sin is what? Perpendicular upon hypotenuse. So perpendicular is BC and hypotenuse is what? AC. So this is first equation. Now in triangle ACD, we have sin R. So again perpendicular, angle, perpendicular, base and hypotenuse. So again sin will be perpendicular. What is perpendicular? AD. What is hypotenuse? AC. So this is second. Now if you divide 1 by 2, why are we dividing? Because we need sin I upon sin R, right? If you do that, sin I by sin R is equals to BC upon AC upon AD upon AC. This AC got cancelled. What we are left with is sin I upon sin R is equals to BC upon AD. Now BC is a distance travelled by the light ray in this medium. So obviously it will be V1 into T. Distance is equals to speed into time. What is the speed here? V1 into T. And AD is again the distance travelled. Right? Now we know that wavefront, the points on the wavefront are at the same phase. So they will travel all the distances all together as they are in the, they will not have any path difference. Why they will not have any path difference? Because they are at the same phase. They do not have any phase difference, right? So therefore, it will be V2 into T. Why I am getting the same time? Again the same thing, that they are at the same phase. This T goes off, and V1 upon V2 we already know that it is equal to mu. So therefore, mu is equals to sin I upon sin R. This we have proved Snell's law. This is Snell's law, which is the second law of refraction. Snell's law, which is the second law of refraction, and we have proved it using Huygens Principle. Now for the first law, we can easily write that the incident wavefront, the refracted wavefront, and the normal all lie in the same plane. Right? So this is the derivation. And you all should remember that you have to write an introduction along with the diagram in order to prove it. Right? Thank you.